Yep. You guys want to flip to your notes? We all good? So in your notes, we all good? Okay. You guys learned the other day f prime of a was equal to the limit as, somebody finish it off. H approaches 0 of f of a plus h minus f of a all over h. Okay. So that's the formal definition for the derivative at a point. We're finding the slope of a line tangent at point A. The fact is that we say the formal definition of the derivative as a function f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Can somebody tell me what's the difference between the one I wrote on top and the one I wrote below? Yeah, so you see the x and the a. Let's talk about what that really means. And here's what it really means, and this is what's kind of cool. Okay? So if I kind of lay this out for you, suppose that we have a function, and suppose the function is equal to 2x to the fourth minus x squared plus x minus 3, or 1, and you want to find the slope at a is equal to 2. We learned how to do that the other day, didn't we? Here's what I will eventually teach you how to do, and it's kind of cool. I will eventually teach you how to do this. You can find the derivative of the function. The derivative of this function is very simply 8x cubed minus 2x plus 1. So if you want to know the slope, all you have to do is plug 2 into that, and it tells you the slope just like that. I will teach you how to do that. I will teach you to where you will start to be able to look at derivatives, and you will know the slope within seconds. That will happen next week. Yep. But before we do that, let's show you what the derivative, so the derivative of that function actually is that. So let's talk a little bit about that, okay? First, other operators that imply derivative, if you see this, dy over dx, that implies derivative. If you see f prime, that means we have a derivative. If you see y prime, that means derivative. If you see d over dx, that implies derivative. Okay. So all of those mean derivative. So what I want to do here is this function itself has a derivative. So today you're going to explore that graphical piece. And again, we won't do an assignment on it, but you will see this piece, okay? And what I'd like you to do is look at this graph right here and take a few seconds. See if you can identify where is the derivative 0. Talk with your partner, those around you. Take about 15 seconds. Where is the derivative equal to 0? Go, talk. Five, four, three, two, one. Can somebody tell me for what x values is the derivative 0? Good. As you look 1, 2, 3, you can see that the derivative is 0 at that spot. So I'm going to write the value of negative 3. The derivative has a value of 0. Okay? Yeah, at 0, it looks like the slope at x equals 0 is also 0. let's I get what you're saying. For the sake of the graph, let's just say at 2. Can we say that? You're absolutely right, though. So look at this function that I have there. It has a derivative. And the derivative I'm going to graph over here. So for example, this is the graph of f of x. I'm going to graph f prime of x. I'm going to graph its derivative. And its derivative has a coordinate of -3, 0. Has a coordinate of 0, 0. Has a coordinate of 2, 0. Now, before we go too much further, I want you to glance at this right here. Does anybody remember what degree this function is? X to what power? It's an x to the 4th power. Okay, you guys remember that from last year, chapter 3 of college algebra? Very good. So let's look at before -3. Okay, let's look over this way. How would you describe the derivative here? It's negative. So that means that the graph will sit above the x-axis or below? Below. Okay, so for example, just to give you an idea, suppose you chose a point, say -4 right here. You would look at -4 and you would say, well, the derivative at that spot, maybe, should we say like, I'm going to say like -5. See what I'm saying? Okay. So the idea is that if you look at -4, we said the slope is about -5. See how everything over here will sit below the x-axis? Because the derivative is negative, so its graph will sit below, saying it has negative slope. What do you notice about the slope between -3 and 0? The slope is always, so it will sit above the x-axis. What do you notice about the slope between 0 and 2? It's always negative. So therefore it will sit below the x-axis, and then after that it's positive, and so it sits above. So this tells me about the slope of that graph. What degree is that equation? Third. So it does always work that the original function of degree 4, that the derivative always reduces by 1 degree. And we can see that graphically. Yes?
How did you get -5 from 4?
I just estimated that at -4, so for an x value of -4, the slope appears to be about -5. Okay, yep, we just kind of made guesswork, okay? Jaya, can you give me a number somewhere between -4 and +3? You choose anything between -4 and +3. She chooses -1. Somebody tell me something about the slope at -1. It's positive. And if you look at -1 here, my graph is above the x-axis. Agreed? Avery, give me a number different between -4 and 3. 2. She chooses 2. At 2, what is the value of the derivative? 0. So if I look over at the graph, at 2, it has a slope of 0. See how this tells me a lot about that. And that's part of what we want to learn today. Now, if you're sitting there a little bit confused, this takes some time, and we're going to have a couple activities we have to do to figure it out. But in order for a function to be differentiable, that means we can take the derivative at point A. Two things must be true. Number one, the function must be continuous. And number two, in order to be differentiable, the derivative from the left, anybody? Must be the same as, yep, must be the same as the derivative from the right. So there are times when you can take the derivative of a function, and there are times when you can't. I'm going to show you the 3 classic examples of where a function is not differentiable. And the first one we're going to look at is this. We've seen that function before, right? You can take the derivative of this function at every spot except for one x value. What do you think is the x value where we can't take the derivative? Why? Because it's discontinuous there, right? So it's discontinuous, so therefore you cannot take the derivative at x equals 1. Another very common graph that you can't take the derivative of at a certain spot would be this graph. How would we describe that type of function? What is that kind of function? It's an absolute value function. Anybody want to guess what spot you can't take the derivative at? You can't take the derivative at 3. Why?
Because it has more than one line to it.
Okay. Say more. What's not the same? The derivative from the left is negative, but the derivative from the right is positive. You see how the slope is not the same for both sides? So therefore, at x equals 3, you cannot take the derivative there. And I'll draw another one here, and this one is a little bit less intuitive.
Is that like a 1 over x squared?
There's no, we don't need to necessarily talk about the actual nature of the function's equation, but you're right to start thinking that way. Does anybody know at what spot you can't take the derivative there? Why? Because you have a vertical tangent. If you were to draw the line that's tangent at that spot, you would get a vertical line. So we call it vertical tangent. Can't do it. So if I could pause again for a second and just look back at the beginning, the things that I want you guys to know thus far is, number 1, every function does have a derivative. So you can look at a graph and determine that. Second of all, there's 2 conditions to be differentiable. And then 3, here's the graphs that are problematic for us, okay? So we really like nice behaving functions. Like calculus really likes those. It works well with those. The other ones, we get to some problems. So this is the heart of what we need to start to practice, which is a good thing, okay? All right? So what I'd like you to do here is just talk with a peer and see if you can see for what x values, ignore the direction, just say, for what x values can you not take the derivative? For what x values can you not take the derivative? Talk. Go. Okay, somebody offer up an x value where I can't take the derivative. -2. How come? Because it's discontinuous at -2. Give me another spot. -1. Why? Different from the left and is the right. When it's different from the left and is the right, we just use the term corner. So if there's a corner on a graph, then we say you can't take the derivative there. Where else? Why? Because you have a vertical tangent there, so can't take the derivative there. Where else? How come? It's discontinuous. Exactly. Try the same thing with the next graph. See if you can identify them again. Go. 2, 1, and here we go. Okay. What do you guys got? First x value. -3 right here because it is a corner. Where else? -2 because it's discontinuous. Where else? Because discontinuous. Some people said 1. They said that looks like a corner. I would not do that to you on the test. After further examination, I would say that does look like a corner. But if you missed that would be okay. Yeah, I won't do that to you. I pulled these offline. I'm going to blame Google. It's easy to blame Google. Okay. All right. And then obviously we have 2 because the derivative from the left is not the same as the right. The derivative from the right we would describe as, we would say barcode, so the derivative from the right does not exist. Okay? And then this one here, you would all say 3 because, you know, as you can see, it's discontinuous. Okay? Good. All right. So here's part of what you're going to have to do on your next test. So this is the skill we want you to be able to develop, and we want you to be able to then engage in activity. So we want to go over these together, then we want you guys to try some things on your own here for a second. It says sketch the graph of the derivative of the following function. So I'm going to put the derivative right on top of here. So a lot of times when we look for the graph of the derivative, it's nice to look for where the derivative is equal to 0. You guys tell me when I get the derivative equal to 0. So I'm going to plot a point on the x-axis there. Where else is the derivative equal to 0? So I'm going to plot there. And it would also be right about there. Everybody agreed? Now, let's think about what's happening before and after those points. Can somebody describe the derivative right here? How would you describe it? It's positive, so I should be above the x-axis, whereas here the derivative is, so I should be below, and then I should be above, and then I should be good. So as I draw this graph, I'm going to draw something that looks like that. Does that look familiar to anybody? Yeah. It turns out that in this case, f of x, the original function, is negative cosine of x, and it turns out that the derivative of negative cosine just does happen to be sine of x. Now, you don't necessarily have to know that right now, but in our next unit, we're going to come up with derivatives of trigonometric functions as well, which tells me, do we need to do a slight trig review in this class, maybe? Yeah. I think that will probably help some people. Let's look at the next one. This one's very, very interesting, and this will keep you thinking. And just to let you know, this is not like I just get it in one moment thing. This can be a little bit challenging. Somebody describe for me that, first of all, is this differentiable everywhere? No. Where is it not differentiable? Right there. So the graph of our derivative will be discontinuous there because we have a problem. So you tell me then, describe the derivative here. Negative. Approximate it. Okay, can we just we'll just agree or agree to disagree. We'll say about -1. Are we okay with that? Do you agree that the slope is always -1? So the derivative will always have a height of -1. Until we get to what spot? 0, then we do not have a derivative value, do we? What is the derivative after that spot? It's +1. So that's what the graph of that derivative looks like. Yeah? Not too bad? Right. Anytime it's not differentiable, you will have a discontinuous derivative. Everybody hear Kaylee's question? Because that's a huge point. Anytime it's not differentiable, your graph will be discontinuous for the derivative. How would you describe this slope? Positive. Estimate it. Okay, let's say it's, can we all just say it's about 1? Yeah. Is it ever not 1? No. Yeah. No. It's like the slope is always, like it's always, you were doing a different problem? Okay, is this slope always, yeah, so it's always, so the derivative of this is this. Yeah.
The derivative is basically this drawn like what results.
Slope. Yep. All right. This is one that should hopefully really draw you in. This is a difference maker right here, this problem. Let's start here. What's the slope right here? So I'll plot 0. Can somebody describe for me the slope right here? It's positive, but it's really, really close to what? Everybody agree that the slope is really small right there? But it is positive. So I'll put a dot right above the x-axis, just above the x-axis. Can somebody describe for me the slope here? It's negative, just barely negative, right? So I'll put a dot just below the x-axis. You tell me when the slope gets the largest. Would you agree that the slope is about as big as it gets right here? So I'll put a dot for its kind of highest spot. How would you describe the slope over here? So I'll always be below the x-axis. You tell me when it's most negative, when it's like it's the biggest negative number that I would get. Okay. Yeah, so I'll put a dot down here. So it turns out that this is an excellent example of the derivative. Kind of challenging to think through, right? It is one of the highest asked questions on the ACT. We're going to do one more together. We're going to leave that one for another day. Somebody tell me this derivative. Zero. Okay, put the notes away. You're going to try this activity. Could you be a helper? Oh, sorry. Yep. Yep. Okay, so what you have is this. Okay. Here's what you want to do. The numbers are the functions. The letters are the derivatives. Try to match what goes with what. Okay? Try to match. You might want to talk with a partner. See if you can do it. Go. Try to match. See what you can come up with. If you want to work with a partner, go ahead.
Oh wait, sorry. So would this one be G?
So you're saying that the slope of that is always 3, or always 2, and G has a height of 2. You are correct. That is G. Good job. Try to get one. Try to get one and move on. Okay. So let's. You want to start with this one? Okay. So how would you describe the slope here? 0. So we're looking for something that goes through 0, 0. So you have that as an option. This is an option. This is an option. Okay. Now, what degree equation is this? Second degree. X squared, right? If you subtract 1 from 2, you get?
-1.
Nope. So 2 minus 1 is 1.
Right.
Okay. So if we do that, so so its derivative is going to be an x to the first power, or a line. What is the slope like here?
Negative.
What's the slope like here?
Positive.
So here's what we've learned. The derivative of this graph is going to be below the x-axis, then it's going to cross over 0, then it's going to be above the x-axis. That'll be this one. We said it's a line. We went from x squared to x to the first. Yes.
Okay, so that one goes with, right? Like 4 goes with G.
Yeah.
Okay, but I that's the only one.
Yeah, I would agree on that.
Okay. So for example, this one here, this one should be a little bit obvious, I'll say. Can you take the derivative at all? Yeah.
Okay.
See that?
Yeah.
So you can move around. But if you look at like number 1, for example, here, okay? If you look at number 1, you can see that. How would you describe the derivative here? It's negative. So you're looking for something that is below the x-axis. What's the derivative here? Nope. 0. So then you're looking for something that crosses the x-axis. What's the derivative here? Positive. Okay? So we're looking for something that's below 0 and above. Nope. Let's think about some other things, okay? What is the degree of this equation? Yeah, x to the second. And I said, what happens when you take a derivative? It's reduced by 1 power. It's reduced by 1 power. So you went from x squared, you're going down to x. So you're looking for something that's just a line that starts down, crosses through 0, and then is above the x-axis. It's that one. Yep.
Why does it do that? That makes it hard.
Well, let me share a little bit more about why it could not be this one that you guys pointed to, okay? So let's talk about why it's definitely not this. So, how would you guys describe the slope right here?
Positive?
I would say it's very positive, right?
Yeah.
Yet this one says it's positive but close to 0. How would you describe the slope here?
Very negative.
But yet here it's.
Okay.
Get my point?
Yeah.
All right.
Sorry.
All right.
I got a lot going on.
I got it. You guys do you. You got it.
Yeah, we have one.
How we doing?
Oh. That's why I meant 7i. 7i. 11. E. Right.
I'll have to show you.
Where do you want me to record it at?
Oh.
That was funny. That was funny. That was funny.
I better get a home computer ticket for that.
She even got her surfer stuff back on. Shh. So A couple people have a couple questions. You guys have started to enter that state of confusion, which is really good. We want to help bring you out a little bit. I'll do a couple of them with you. Which one would somebody like to look at? You're like, you know what? That one's kind of 6. Okay. 6 is an excellent example. This is our function, and what we would like to do is we would like to find the derivative. And so all I have to do is I really just have to look at a couple pieces, okay? Number 1, how would you describe the slope right here? Oh. Six is a great example, as well as 10. Is that what you said? You want to look at 10? Okay. All right. Number 10 is a great example. Okay. How would you describe the slope right here? It's 0. So you know that the derivative is going to go through 0, 0. How would somebody describe the slope right here? Would you agree? I'm not just going to say negative. I'm going to say like super negative. Would you agree? So if the derivative is super negative, it's going to be sitting way below the x-axis, right? So you're going to look for something down there. Okay? Now, how would you guys describe the slope right here? So it's going to be sitting way above the x-axis. Now, hold on. One last thing. Okay? Hey, Sid, eyes up here, okay? Does the graph ever go over to -3 or to +3? So its derivative will never go over to -3 or +3. That should be able to help you see that. Does that help a little bit? The answer is L. Yep. For the one we just did. Yeah. Okay, folks, if we could look at problem 1, this is something we talked about. Hopefully this can make sense. Let's look at problem 1. What's the derivative right here? It's 0, okay? Describe the derivative here. It's negative. Describe the derivative here. It's positive. Now, although L is a good choice, it's not the choice. And here's something I was trying to tell you earlier. What's the degree of this equation? This is x to the 2nd power. Everybody agreed? I told you what happens when you take the derivative. It goes down by... So what graph does x to the 1 power make? So you're looking for a line that starts down here and ends up there. Yes.